metabolism by talking about metabolism, and then we're going to just very briefly, on a summary table effect concept, look at the effects of hormones on the levels of fuel, amino acids, fatty acids, and glucose in the body. So this first slide that we kind of skipped over rather quickly on Thursday is a summary of, you can see at the top, proteins and carbohydrates and fats in their role as a fuel source and where they're absorbed and what happens to them. And we're focused on this middle area here of carbohydrates, all right? And our most common carbohydrate is glucose, as far as the simple sugar is concerned, because every disaccharide had at least one glucose in it. Sucrose had one glucose in fructose. Lactose has one glucose in lactose, all right? And maltose has two glucoses. So on Thursday, we did glycolysis. And glycolysis on your lecture notes is on page 56. And we took it through the intermediate step. So, remember glycolysis was anaerobic? And it took place in the cytoplasm of the cell rather than in a particular organelle. That's where the enzymes are that regulate it. And we start out with a 6-carbon molecule. Whether it's glucose or fructose or galactose, it's all 6 carbons. We added phosphate to it and removed hydrogens. And our final product ended up being, and I'm not going to put the numbers down here, ATP. Remember, we had a net gain of ATP. We broke a carbon-carbon bond, but we did not make carbon dioxide. We just split the bond in the middle. So our final product of that, we converted glyceraldehyde to pyruvic acid. We captured the hydrogens that were removed from glucose as a result of forming glyceraldehyde and pyruvic acid, and we transported those on molecules, our coenzyme molecule. Okay, so those are the final products of glycolysis, and we always have heat. Okay, so I'll just stick that in there. Then we took off the, yes?
For the exam, will we just need to know what the products are or how much of each?
The products, okay? Then we took pyruvic acid. So this was glycolysis, and we did the intermediate step of the mitochondria. And this was the first time we actually released carbon dioxide, okay? So the products of our intermediate step were carbon dioxide. Any ATP? No. Okay. And our coenzyme transporting the hydrogen. Okay. And of course, heat. So we're now ready to move into the citric acid cycle. But I want you to recognize that even though we haven't made very much ATP, we haven't captured very much energy yet, it is the energy level of the hydrogens that are going to provide us with the maximum amount of energy stored as ATP. So it seems like we're kind of plodding along here, but we're still capturing these hydrogen molecules, and that's where most of our ATP is going to come from eventually. All right? So now we're in the mitochondria. And we're ready for the citric acid cycle. So if you look at the organization of the mitochondria, I know it's been a few months since you did cell organelles. Mitochondria are often drawn as an oval like this, but they can be round, or they can even be T-shaped. Okay, it's just, they have those varieties of shapes. And often the inner membrane is just a shelf like this, but it can also be tubular, like a long cylinder, but this is the most common form. This space is known as the outer matrix. This membrane is known as the crista. And then this space in here is the inner matrix. And that inner matrix is where the enzymes are found that regulate the steps of the citric acid cycle. Okay? They're solubilized in the fluid of that inner matrix. These enzymes, because they are found within a membrane-bound molecule, are transported there via a vesicle that has pinched off of the Golgi. So these are enzymes, unlike glycolytic enzymes, that have been processed via the ribosomal ER and the Golgi apparatus. They had a destination. They were just allowed to roam free in the cell. Now, any idea why it's identified as a cycle? So we've drawn it in a ring here with each of the subsequent reactions.
Goes over and over.
All right, it occurs over and over. We do not have rings of enzyme in our inner matrix, like little fairy rings inside the mitochondria. These enzymes are all mixed up, okay? So the substrate is not going to go in a nice circle as it goes from around and around. It's just whatever enzyme the substrate happens to meet that's the next effective one that it will react with, right? So the reason it's a cycle is because our product, oxaloacetic acid, is one of the first reactions that are formed together. So by the time it goes through all these reactions, we end up forming the beginning of the next reaction again. That's why it's called a cycle. Now remember I said for each of these events that there would be a summary at the end of each component that tells you what you need to know. So on page 56, page 57, at the bottom of the page is the summary for the citric acid cycle. And nowhere in there does it list any of these other molecules. Okay? The only molecules that are listed that you need to know are the acetyl group, the oxaloacetic acid, and the citric acid. So you don't need to know these other molecules in sequence, but I want you to understand what is happening during the cycle. Okay? So that's what we're going to go over now on the board. So the 2-carbon molecule, our acetyl group, that has been brought to the mitochondrial matrix by the coenzyme A, separates from the coenzyme A. And it binds with a 4-carbon molecule. And again, oxygen and hydrogens are part of this molecule. We're just not paying attention to that part of it. Known as oxaloacetic acid. Again, this is enzyme regulated. And this forms a new 6-carbon molecule, which is not glucose, but is known as citric acid. Well, I thought we were trying to break down our 6-carbon molecules, and here we are with another one. Right? But this allows us to enter into the sequence of actions, and what I'm going to draw on the board is what happens. So the citric acid is modified to form isocitric acid, and then we start to actually remove components from it. So carbon dioxide is formed. The loss of our 3rd carbon. So whenever we split off a carbon, it diffuses out of the cell as carbon dioxide. Okay? When that carbon is lost, additional hydrogens are lost and bound to a coenzyme, which is going to transport them to the crista of the mitochondria. Again, so this forms a molecule. All right? Again, we lose a carbon as carbon dioxide and capture the hydrogens that are released by our coenzyme. Form another molecule. Enough energy is released that an energy storage molecule is produced known as GTP, or guanine triphosphate. That has the same energy form as ATP, so it's considered to be the equivalent. All right, so I'm just going to put in parentheses ATP. We continue forming new molecules releasing hydrogens, and those hydrogens are captured by additional coenzymes. So we've added a new coenzyme in here. And then finally, we're back to oxaloacetic acid. So in the citric acid cycle, we've released 2 carbons. That brings us back to 4. And we've captured additional hydrogens that we're going to use in our next activity, electron transport. And we've produced about the same amount of ATP as we did with glycolysis, only this won't occur unless we have oxygen available. Now notice I've gone through 1 time, but for a molecule of glucose, this whole process occurs twice. It can be occurring at the same time, all right? It doesn't have to, the other acetyl group, because remember we have 2 acetyl groups. So we had 2 pyruvic acids that were 3 carbons. We made 2 carbon dioxide molecules in our intermediate step. So now we have 2 acetyl groups. So this whole reaction is going to occur twice for every glucose molecule. All right? And that one's not just sitting there waiting around for this one to get done. Those reactions are probably occurring at the same time. Just as an interesting point, these first 2 carbons that come in for the acetyl group are not the same carbons that are lost the first time when carbon dioxide is made. This reaction has to occur several times for those actual, we're going to tag them with radioactive material before we'd actually see the carbon dioxide be radioactive. So eventually those carbons will be lost, but the number is still accurate. We add 2, we lose 2. Okay? So our product, oxaloacetic acid, is the same as one of our original substrates. That's why it's called a cycle. It keeps driving itself as long as we have additional carbons coming in. So it's not very high in energy production if we have just glycolysis, because we produce the same amount of ATP as we did, as we have just citric acid cycle, because we produce the same amount of energy as glycolysis does. So we haven't produced very much yet. 4 of the 38 that are going to be produced. So the most energy producing, most AT producing step is the electron transport. Okay? And that's the last sequence, the last activity. So before we leave this, what would be the final products of our citric acid cycle? Carbon dioxide, NAD, H2, oxaloacetic acid, so it goes on, and there's a final product again, and of course, heat. Okay? Oh, and GTP. Okay? So the concepts again that I want you to take away from the citric acid cycle are listed under the summary. And all of that information is up there on the board as well. So this takes place in that inner matrix, and now we're going to be using the entire mitochondria. The inner matrix, the crista, and the outer matrix. Right? The significance of the outer matrix of the crista for our mitochondria and electron transport is that that's where the enzymes are found. They're actually, that is within the membrane. So remember how sucrase was embedded in the microvilli membrane? So these enzymes are embedded in the plasma membrane crystal. But before we get to that process, I want to talk about reduction oxidation. Okay? And so what we have here are a series of enzyme complexes, some of which are NAD and FAD, some of which is ubiquinone or cytochrome B, cytochrome C, cytochrome A. And you have a series of, most of these are written on page 60. But I want to talk about, first of all, before we go through those, what an oxidation reduction reaction is. So let's take the NAD, all right? NAD is our coenzyme. And I'm going to illustrate it and then we'll define it. So NAD is our coenzyme. When we go through the intermediate reaction and we remove a carbon dioxide, or we took glyceraldehyde and converted it to pyruvic acid, hydrogen molecules were released. So here comes hydrogen, and we bind it to NADH2, and that addition of adding the NADH2 to adding the hydrogen to the NAD is considered to be, when we add that, we are reducing the molecule, all right? So then the hydrogen is removed. Maybe I should do the sequence I do it, the diagram, I have it on here. Okay, so then the hydrogen is removed, and it's now deposited, or a chemical bond is formed to another molecule, and it's added to another molecule. When it's taken off, that process of removing it is called oxidation. So this molecule is reduced, this molecule is oxidized. So this would be the oxidized form of NAD, and this is the reduced form. The next molecule that can accept that hydrogen, and bear with me and it'll make a little bit more sense, is FAD. So the hydrogen is now bound to the FAD, so we have now reduced FAD. All right, so the addition of the hydrogen to FAD means that FAD is now reduced. Why does hydrogen move from the NAD to the FAD along our crista in the inner matrix? So if this is our mitochondria again, and here's our crista. Again, these can be moving around, so just because I draw them side by side doesn't mean they're physically side by side. But here would be NAD, here would be FAD, and the hydrogen has been transported to the FAD, oxidizing the NAD, reducing the FAD. Why would that happen based on the little bit of chemistry that we've talked about? Why did bicarbonate, when we talk about carbonic acid, why is hydrogen more likely to leave the chloride and hydrochloric acid than it is to leave the bicarbonate ion and carbonic acid? Remember the term we used? Affinity. Okay, was that what you were going to talk about, John? No. Okay, did you have a question? Or? All right, so FAD has a higher affinity for the hydrogen than NAD does. Okay? The next molecule in the sequence, I don't have it on your page, the quinone, so I'm just going to skip that one and switch to cytochrome B. Cytochrome B has an iron ion that accepts or gives off electrons. So after the FAD, cytochrome B is going to have a higher affinity, and the hydrogen is going to leave the FAD. Okay? So this is the oxidized form, this is the reduced form, and now our hydrogen ions are going to split and form a hydrogen ion and an electron. And now we're just moving electrons, which is why this whole process is called electron transport. All right? So the electron is going to be added to cytochrome B. And originally cytochrome B has 2 positive charges, but the electron, when we add it to it, is going to neutralize one of those and change it, reduce it from 2 positive charges to 1 positive charge. Okay?
Wouldn't that be oxidation?
Reduction. Then, cytochrome B, that electron is removed, and we have 2 positive charges, and this is oxidation. So taking away the electron. Oxygen wants electrons. So when we oxidize something, we take electrons away from it. So oxygen would remove electrons. It has a higher attraction for those electrons. So again, this is the reduced state. This is the oxidized state. So the reduced state is when there's fewer, we reduce the number of positive charges by adding electrons. All right, there's another way of remembering the oil rig phrase that some of you might know. So this is the oxidized state when the electron is removed. Okay, so this is reduced when we add the electron, we take away the electron, and now we're back to 2 positive charges. We've oxidized that molecule. So for those of you, oil rig, oxidation is loss of electrons. Reduction is gain of electrons. So I personally think about it as reducing the number of positive charges by adding the electron, but either way, whichever helps you, okay? So oil is oxidation is loss of electron, rig is reduction is gain of electron, or the hydrogen atom itself. It works either way. Okay, now, I have a little story to tell. Not very flattering for women. So for those of you watching on video, I apologize. But a lady goes into a bar. Well, she doesn't act like a lady, but anyway. A woman goes into a bar. And she seems to be pretty attractive to the men that are there. And they keep coming and talking to her and trying to pick her up. And finally, this one guy shows up, and they just click. She's interested in what he does, he's interested in what she does, and he laughs at her jokes and vice versa. She goes home with him. Okay? The next morning when she wakes up, we won't talk about their sleeping habits, I don't know. The next morning when she wakes up, he brings her breakfast in bed, and in this crystal goblet of orange juice, when she finishes drinking it, are 3 10-carat diamonds. And he says, I've got to go to work, but I know it wasn't very flattering to the woman. There's a helicopter out on the pad. Pilots at your disposal. There's 3 Jaguars in the garage. Here's all of my credit cards, platinum and titanium, whatever. You can just go do whatever you want to, and I'll see you tonight. Well, this is really nice. I mean, she likes the guy, plus he's spending money on her. What more would you want? So, but he's gone all the time. And after 2 or 3 weeks of this, she gets lonely. She finds herself back at that bar. It worked for her the first time. So she's back at the bar, and it might take a couple of nights, but she meets another guy. And boy, he is even more interesting than the first guy. And he goes cross-country skiing, which she's never tried before, and she's anxious to try, so she just totally forgets about the first guy, goes home with the other guy, leaves her Jaguar at the bar. And the next morning when she wakes up, instead of diamonds, she only has rubies. Okay, no helicopter, a couple of Mercedes out there, and not as many credit cards, but she doesn't mind because this guy stays around a little bit more, and they have fun doing stuff together. She doesn't miss the money. He seems to have enough to take care of her. She doesn't know that he has just as much money as the other guy. He's just not spending it on her, and she doesn't mind because they're having fun. Well, not as much fun as she thought. Because a few weeks later, she's back at the bar again, and she goes home with a guy that, it's not even a BMW, it's just a really nice Saturn. And they take road trips. But she's learning so much about this guy. He's so much fun. He's encouraging her to write and do things that she's never tried before. She's really attracted to him. She doesn't miss the money. See what we're doing? Attraction is affinity, all right? So each person that she goes home with, she has a greater affinity for. So each of these molecules along the membrane has a greater affinity for the electron. But it doesn't need to use as much energy to hold on, or money, to hold on to that electron, all right? So the decreasing levels are showing the energy levels. Now, the next picture shows the Krista. Here's the first guy. He's taking some of his money and is using that energy that was left over by this person, not needing to hold on to her, and pumping hydrogen ions from the inner matrix to the outer matrix. It gets active transport. The next molecule, also, finally we split the hydrogens and now we're just moving electrons, but we still have enough energy in between these molecular complexes to pump hydrogen ions from the inner matrix to the outer matrix. Finally, to get back to our story, she meets a guy. He's fun. He's just not quite her type, okay? So she goes back to the bar, and now she's found her soulmate. So she leaves this guy. She goes to the bar. She meets this man. He comes up in a bicycle, okay? And he said, I've got this great place on the beach. It's just a shack, but I've got a sailboat. And she says, I know how to surf. I don't know, we don't need a sailboat to surf, but you can teach me how to sail and I can teach you how to surf. And they end up on the beach. A bicycle, a surfboard, and a sailboat. But what else do you have on a beach? Water. Water. Yes, water. Fan too. But these two electrons get back with their hydrogen ions and half of an oxygen molecule, lowest level of energy. All the energy from these electrons has been given up going through each of these successive chemical reactions. And the final product, water. Lowest energy level, highest affinity for the hydrogen. Okay?
Is that half O2?
Yeah, because it's just one oxygen atom for water. So half of an oxygen molecule. All right, so that's what happens to the hydrogen and electrons. Remember we were using that extra energy that was left over between each of these relationships and buying CDs and islands in the Caribbean and so on? Well, in the cell, that extra energy is used to move the hydrogen ions from the inner matrix to the outer matrix. Now we've got a high number of hydrogen ions in the outer matrix. If we were to open up a channel, what would they all do? Diffuse down into back to the inner matrix. So the cell provides a channel for that. A hollow protein that contains a channel for hydrogen ions. Interestingly enough, when those hydrogen ions stream through, it causes a rod in here to spin. And that spinning rod is a really cool kind of bioengineering. That spinning rod activates sites along the lower portion of the protein that are enzymes, and phosphate is added to ADP. There's enough energy from all of these, from a hydrogen. If we start at the NADH2, there's enough difference in energy between this level and this level to pump sufficient numbers of hydrogen ions into the outer matrix that when they come spinning through, there's enough energy to make 3 ATP molecules. So for the hydrogen that's bound to the NADH2, and then again, you don't have to memorize these numbers, but just talk about the amount of energy that's there. The difference in energy between here and here is enough to make 1 ATP molecule. The energy that's between, so if we go back to those enzyme complexes, the energy that's between the cytochrome B and cytochrome C is enough to make another ATP molecule, and the energy difference between cytochrome C and cytochrome A sub 3 is to make a third ATP molecule. So for all the hydrogens that are bound to coenzyme N18, we get 3. If the hydrogens are bound to FAD, we only get 2, and that's how the math is done. Okay? Again, you don't have to worry about those actual numbers, but just explaining because of the energy levels on the electrons or the hydrogens. So on page 62, on the summary, the end product of carbohydrate metabolism, that's carbohydrate metabolism. What would be the end products of just electron transport? ATP, water, and always heat. Okay. So if we look at all of those final end products for glycolysis, for the intermediate step, for citric acid cycle, and for electron transport, our final products of glucose catabolism, obviously ATP, and water, carbon dioxide, and heat. Okay. So we have pyruvic acid as our final product for glycolysis. Why isn't it a final product for our entire activity? The pyruvic acid is broken down in the intermediate cycle. Okay, so that's why some of those that were end products of subsets of the whole thing are not end products of the final stage because they are further mobilized and don't appear in our final product. Okay. Now that's carbohydrate metabolism. What happens if we have too much glucose? This is on page 64. So glucose anabolism, if we take glucose molecules, so this morning I had to stop at the grocery store and buy whipping cream for our lab activity. And while I was in there, I picked up some pastries for the kids. Savannah didn't eat anything. Will only ate one. I was surprised. I'll probably have them all gone by the time I pick them up today. So let's say he had no lunch. He forgot his lunch. So he ate 2 donuts and a Danish for lunch. What do you think his blood glucose levels will be about an hour later? They're going to be up, okay? So this excess level of glucose, the body tries to maintain homeostasis. So this extra level of glucose in the hepatocyte in the liver cell is going to be synthesized into polysaccharides or glycogen. All right, that's anabolism. That's not breaking down the glucose, it's reforming it back into starch. And so then, let's say that I don't pick them up until 6:30, and my daughter's driving home today for the first time. She had her first in-car driving lesson on Sunday. So she's not ready to drive on the freeway. It might take us a couple hours to get home, so the normal 40 minutes. So let's say it's 7 o'clock before he gets home. What's going to be his blood glucose levels? They're going to be pretty low, all right? So we'll be talking about the hormones in a few moments about what happens, but that's going to trigger the liver to release the glycogen as glucose. And so all of these steps are reversible, including this very last step, adding that phosphate to the glucose. Remember I said most body cells don't have the enzyme to remove that, but the liver does. So now this glucose can be released into the blood to maintain an elevated blood glucose level. So we have a couple of terms here. So glycogenolysis and glycogenesis. Glycogenesis is taking glucose and forming glycogen, which is a starch. All right, so formation of glycogen is glycogenesis. The reverse, taking glycogen and releasing individual glucose molecules, is glycogenolysis. All So the two hormones that are important in regulation of this activity are what? When blood glucose levels are elevated? Insulin. So this occurs in what we call the absorptive state. And it uses insulin. And this occurs in what we call the post-absorptive state. And utilizes glucagon. Okay. So several hours, 2 to 4 hours after you eat, we start the post-absorptive state. Now other fuels can be used. So if the body is under stress, glucose tends not to be used. All right. If the body is using growth hormones, glucose tends not to be used, and proteins and fats are broken down and used instead. So that process of using different fuel sources, lipids and amino acids, is known as gluconeogenesis. So using fatty acids and glycerol, or using amino acids. For fuel. We can still use our citric acid cycle. If we go back to this very first slide, all right, amino acids, well, we have lipids up here. Fatty acids can come in as acetyl-CoA. Glycerol can come in as glyceraldehyde, so into glycolysis. And amino acids can come in as glyceraldehyde or into the citric acid cycle as well. So here's a diagram for lipids. So the glycerol can be converted to glyceraldehyde and come in at the very end of glycolysis. Fatty acids can be broken down into acetyl groups and come into the oxaloacetic acid. So when we have a long chain fatty acid, it can be broken down into 2 carbon groups, and that's our acetyl group. Body doesn't know the difference. This process is known as beta oxidation. Okay. If it doesn't occur in a very complete form, we get ketones, and that's how diabetics get ketoacidosis, is that remnant of that acid part of the fatty acid builds up. So here's beta oxidation, and we bring in the acetyl group, and that can also go into the citric acid cycle. Okay. And you have this diagram on page 65 of your lecture notes. Proteins, I don't have a separate diagram for that, but proteins can go into the glyceraldehyde, or they can form pyruvic acid, or it can go into the citric acid cycle as well. So that's gluconeogenesis. We either don't have enough carbohydrates, so if you're on a low-carb diet, this is what your body's going to be using. Okay, the fatty acids and the amino acids and glycerol instead. In fact, if you certain high protein, low carbohydrate diets will ask you not to eat any fruits, any carbs, and you can use a little dipstick like we used in lab for our urinalysis and test your urine until the ketones bodies show up, and that shows you're breaking down fats, and then you can start adding small amounts of certain carbohydrates to your diet, but they want you to stay away from any carbs until those ketones show up. As a vegetarian, that is totally impossible. I've tried it. Do not eat fruit for the amount of time it takes for that. And if you don't eat meat, the amount of protein, you're eating all the time and chewing, and it's like totally boring. So I cannot go on a non-carbohydrate diet as a vegetarian. All right, so I want to look at a couple of terms. On page 68, it talks about the absorptive state and the non-absorptive state. All right, so what I wrote over here, glycogenesis is going to occur during the absorptive state. Glycogenolysis during the post-absorptive state, meaning 2 to 4 hours after you eat. And it makes sense. So right after you eat, you're going to have elevated levels of glucose and lipids and amino acids. All right? And your body is going to take those up. And then 2 to 4 hours after you eat, if you haven't eaten again, you're going to have low levels. And so the body is going to start releasing these components. And that's what we're going to look at after our first break for a real brief discussion. Maybe we won't take a first break. But anyway, at the very end for the regulation of hormones. Okay? So we'll review what insulin and glucagon do, but we've really already discussed those. So what I want to do now is just define a few terms that are on page 72. Most of you have seen these words before. You've taken a nutrition course. So these are all in uppercase letters. But if we define calorie with a little c, what is the nutrition definition of calorie?
Isn't it the amount of energy needed to raise a certain amount of water, like 1 degree or something like that?
Yes. And the amount of water would be? 1 mil.
Yeah.
Okay? So this is the amount of energy or heat measured in British thermal units required to raise the temperature of 1 mil of water 1 degree Celsius. Okay? Now a kilocalorie, kilo means what value? 1,000. This is also written as an uppercase C. When you look at a box of food, cereal or whatever, it says, half a cup of cereal is 110 calories. Which one are they talking about? The bottom one, okay? So the kilocalorie. So would that be to raise the amount of energy required to raise the temperature of 1,000 mils of water? Or to raise the temperature of 1 mil of water 1,000 degrees, or does it matter? What does water boil at? 100. So we could never get to 1,000 degrees unless we changed atmospheres. All right, it would just boil away. We couldn't raise it any higher than that. So a kilocalorie is the amount of energy required to raise the temperature of 1,000 mils, or a liter, 1 degree. Okay? Basal metabolic rate is the number of calories that you need in your body to maintain your cells at a living wage. In other words, you can't lie there in bed and do math, or speak, or blink your eyelids. Okay, just enough to stay alive is the basal metabolic rate. Anything else is added to that. It's often given as an average of about 1,200 calories, but a lot of people need less and a lot of people need more. Okay? So I typically take in probably about 1,000 calories a day, and I do more than lie in bed and blink my eyelids. Other people would lose a pound a day if that's all they ate. Okay, so it varies from individual to individual, also dependent on their body mass and on their hormonal levels. What's the difference between malnutrition and malnourishment? Are they the same? They're not. I'll just tell you that up front. If I ate 1,500 calories a day, could I have malnourishment? If I have my normal everyday activity, 1,500 to 1,800 calories, would that fall under malnourishment? Probably not. What about nutrition? If it was all candy bars and ice cream? Probably yes. All right? So malnutrition has to do with the proper balance of the fuel sources, vitamins, and minerals. So you have a proper balance of lipids, carbohydrates, and protein in your diet, and the adequate amount of vitamins and minerals that your body needs for coenzymes and all of that. So you could have adequate calorie intake, but if all you ate was baked potatoes, all right, you wouldn't be getting all the other sources of body amino acids and lipids that you need. Malnourishment let's say you drink 3 liquid meals a day and you take a bunch of vitamin pills. So you're getting all your adequate carbohydrates and proteins and vitamins, but not enough calories to maintain normal activity of your cells. All right? So this has to do more with caloric balance. Too many or too few. Either way is malnourishment. Okay?
But that's only when like you're out of fat that can be converted into calories, right?
Well, so it's not just lipids and carbohydrates. It means you're getting the normal amount of recommended daily requirement of proteins and lipids and stuff, but not sufficient or too many. Either way, for your body. Improper, thank you. I'll just take away the word proper. But yeah, it would be improper and this would be imbalanced. Thanks. All right, now, we will take this a short break, but before we do so, we have a situation that I'm going to give you. A plane has crashed in some remote desert location, middle of an Arctic island, I don't care. The pilot is a 30-year-old woman.
Eat her first.
She weighs 320 pounds.
Oh, yeah.
She is 5'7", and she just won the national bodybuilding contest. I'm not sure you would eat her first. If you could get to her.
Wait until she's asleep.
You might make some nice steaks. All right, she has a 3-month-old baby.
Only her.
Thinking twice about eating her. Her 92-year-old grandfather is on board.
Good. Who's going to taste like dust?
If you're not careful, we might soon be dust. And her 15-year-old brother, who is about 425 pounds of adipose tissue.